just to get started, we are sitting in a classroom at the Waterpower Lab, and we are going to, the three of us are going to give you a tour about at least two projects that is ongoing in RenewHydro right now. So I'll be the one introducing the project, and then Amul Ghimire, who is a PhD working on cavitation on Turbine, will be one that doing the that will talk about cavitation, and then Francesco, who will talk about fatigue loss, and try to answer maybe one of the main questions that are most often asked questions that we are receiving here in the lab. What is the cost of flexible operation? So let's dive into the project. We have only 45 minutes to do it on, and I hope we are able to do it within that time.
It's good.
Thanks. So in RenewHydro, we have one project called the Reversible 1.1, which is about new hydropower plants, design and constructions. And Amul, who is going to talk about this project, is looking into the submergence of pump turbines. And the question that is, the research question is, can we reduce that submergence? That's a big question. Here is, just to give you an introduction to it, here are different turbines, pump turbines around the world with different submergence. And here you see submergence down to 70 meters that is being that is utilized today. So, but you see it from just a few meters down to 70 meters, and we see new pump turbines is coming with a fairly large submergence, and of course, if we can reduce that submergence, the cost will be also reduced quite a lot. We are looking into Sira Kvina Hydropower system and to Tonstad as a case study. Tonstad or Sira Kvina is going to look into the possibility of building a new pump turbine from Sirdalsvatn up to Gravatn, and with a fairly large power output. And this is one of the cases that we will look into this project. And it's quite when they are giving us all the information from that power plant. So it's a nice thing being in RenewHydro that can give us access to data about these things. I'll give the word now to Amul so that he can show you what he's doing in his project. So Amul.
Yes, thank you very much, Ula. Hello, I'm Amul Ghimire. I'm a PhD candidate here, as Ula introduced. And I am working on the topic submergence of reversible pump turbines. And this is, as already introduced, under research program 1.1, and it's activity 1A6 within that research program. And the main objective is to find the possibilities for reducing submergence of reversible pump turbines. I will be talking about what this means and how it is a big topic right now. So first we have to talk a little bit about cavitation, and like basically just defining it. It's a way of when water changes its phase from liquid to vapor because of drop in pressure at a given temperature, then we can call it cavitation. And it is not a new topic, and it's not something that we just discovered. It's been around for many years. It was first coined by Rudd, who actually found it on ship propellers, and it was in 1895 that it was first introduced to the world, and it's still a big problem in the hydraulic machines in daily operations. And to define it and to understand it a bit more, what we have to understand is boiling of water, because cavitation is just basically boiling of water at room temperature. So what happens is when you are boiling water at sea level, where the pressure is 1 atmospheric pressure, around 100 kilopascals, you boil water at around 100 degrees Celsius. But then if you go up above like several hundred meters into the mountains, you can actually boil water. The water will start boiling at much lower temperatures. And to see that, Yeah, and to see that we get into this phase diagram of water, I won't be talking much detail, but where we need to look at is around here, where we see vapor and liquid or phase of water. So what happens is when we are at around atmospheric pressure, we have the water boils at 100 degrees Celsius as shown in the graph. And at around 3000 meters above sea level, it's boiling around 93 degrees Celsius. While if you want to boil water at 20 degrees Celsius, meaning at room temperature right now, what we can also do is decrease the pressure of the vessel to 2.1 kilopascals. So this is like 2 centimeters of water column. So this is when the water boils at room temperature. And if we look closer into vapor bubbles, what it does is the liquid water turns into vapor, and then if its surrounding is at higher pressure, it will actually implode within itself. Like for example, on this video, what you're seeing here is a vapor bubble or cavitation bubble being formed because of laser being shot at very precise location, which is close to the surface of the water. And at this point, what happens is the bubble forms, and the weakest point here is the surface of the water. So the implosion is being into the water. So when this implosion happens, you will see that there is a jet that's coming down, and then there is also shock waves together with that. So it's both the jet and the shock waves that will hit on your surfaces. In our case, it's the turbine surface, blade surfaces, which causes damage to the turbines, which is why cavitation is something that we need to consider while designing. So, and going into the turbines now, what happens is so cavitation happens when the pressure is very low, and in a turbine, when the pressure can go very low is when it can go very low is when the flow is disturbed and when there is flow separation, and flow separation happens when there are obstructions on the flow. So it's all right. Yeah. So we will look at this later as well. So now going into the pump turbines, talking about pump turbines, what these are basically just Francis turbines, which has a runner that looks more like a pump, and it's designed to operate both as pump as well as turbines, such that it can pump water back up to its upper reservoir. So for example, if you were to operate the Francis turbine as a pump, it will pump up water, but not all the way up to the same height that you would actually want your upper reservoir level to be. And then talking about cavitation, so I could not show you video before, but what happens is when the at best operating mode in turbine mode, the relative velocity of the water is flowing aligned with the shape of the blade at inlet. And if, for example, if we are looking at high flow, what happens is this relative velocity will not be aligned in the same way now, and it will be hitting on the blade a bit on the offset. So because of this, you will see flow separation on the opposite side of the blade. And when there is flow separation, there is pressure drop. And when there is a pressure drop, there is a possibility that you could go into the cavitation region of water at that temperature. And we did this test in the lab and saw that we could, when operating at low enough head and with really low suction pressure at the suction side, we saw that we cavitated on the at the inlet of the turbine itself in turbine mode. You can also see this on the video. So this is the suction side of the blade being cavitated when the flow is like when we are operating at low flow or part load. And again at sorry, that was full load, and this is part load where you see that the cavitation will be occurring at high pressure side of the leading edge right here. And then it's not at not just at the inlet of the runner that you see cavitation. There is even more cavitation at the outlet where the pressure is even lower. So we see these kinds of cavitations in the outlet of the turbine mode. And looking at this, it doesn't look like much because these are like way better operating conditions. But if you are going much deeper into the off design conditions, you see this, which is that you don't see anything. It's only cavitation in there, and this is accompanied by lots of vibrations during operation, and possibly damages if we continue running it for a long time. Now looking at the pump mode operation. So pump mode operation is nothing but rotating the pump turbine runner in the opposite direction of the turbine. So at best efficiency point, what happens is that the relative velocity, same as before, should be in the same direction or aligned to the shape of the blade. And as soon as there is any differences in this alignment, we see that flow starts separating, and it's much easier to see cavitation at this point, so at inlet of pump turbines, because the whole region in that area is at really low pressure unless you pressurize it. So this was at design conditions. Actually, what happened was we reduced the pressure so low that we saw cavitation at design conditions. And I said that if the flow conditions are aligned to the shape of the blade, we should not see flow separations. But because of the thickness of the blades itself, we cannot have infinitely thin blades. So as soon as there is some thickness, it's obstruction for the flow, and that causes some flow separation, causing these kind of cavitations. And as soon as we lower the flow, so this is when you have your upper reservoir quite filled up, so it's close to your, let's say, higher regulation level, and you're still pumping up water. So this is what could happen in your pump turbine in pumping mode. So this is low flow and high head operating conditions. And this is also accompanied by lots of noise coming from cavitation as well as vibrations. While this is at high flow, when you have less water in your upper reservoir and you're pumping more water through your pump turbine runner, and you see cavitation here, it doesn't look much more damaging as it is here. But if you look at the other side, at the outlet of the pump mode at the guide vane, you would see this kind of cavitation. And we looked at vibration signals from the guide vane during the same operating condition that I showed you last, and we saw pretty good in frequency regime that there were quite good segregated frequencies. So what we believe is that this high frequency region here could be cavitation, but we need to do more analysis to be 100% sure with that. But what we could also see clearly are the rotational frequency here, and then we had blade frequency. Like each time the blade passes the guide vane, there is a peak, and that was also seen like many different multiple harmonics of that were also seen. And if you were here during this test, you could see that the sound coming from this turbine sounded more like a turboprop propeller when it was running. So in order to reduce this, in order to avoid cavitation, the method is to increase the pressure at the inlet of the pump mode. And to do that, we need to submerge the turbines quite deep, as Ole already mentioned before. And submerging this deep means lots of investment requirement, and we need to spend a lot of money, as well as technically it needs to be very sound to be able to like submerge everything so deep into the mountains. So it is a challenge to submerge it, which is why we are working on this topic to trying to reduce submergence. And to be able to understand, be able to reduce that, first we have to be able to predict what would be the requirement of a pump turbine to be submerged, or which is predicting required NPSs, which is another way of saying submergence, as it's one of the component in calculating these NPSs. And there are many different ways the literature has suggested that this can be calculated, and these are all the methods that are available out there, and we don't know if any or all of them could work in our case, which is why we are doing this ourselves by using experiments. And what we see is that as we decrease NPSS or cavities trauma number, what happens is the head drop starts quite late or like very very low pressures. So we did so this is at 3% head drop, and the cavitation is very high. So we would not want our pump turbines to be operating at this point. And this is when you have submergence equivalent to nothing or equal to the level of the tail race for a 500-meter project scaled up from our pump turbine. But then if you are looking at 0.2 Thoma coefficient number, which is equivalent to 80 meters of submergence for a 500-meter project, we still see some cavitation, and our target is to find a location somewhere in between here where we won't be cavitating so much that the damage is uncontrollable. And that is what we are currently working on, finding a way to say how much damage it could cause or how long we can operate with some level of cavitations, if like by reducing the submergence. And apart from that, we are also working on creating a numerical model for predicting or like simulating cavitations in our original design or our original pump turbine that we have here, which is quite close to what we have seen in the experiments right now. We will be continuing exploring this and then start making changes in the designs and see or like optimize the designs to reduce cavitation by working within the same level of submergence that we are seeing cavitation in our current design. And we have done lots of experiments right now, and I think I have more than enough data to be able to trapped in my cave for several months, analyzing them, and we will continue exploring everything like videos as well as vibration data and other performance data we have, and we will find explanations for different cavitation behaviors, comparing them with numerical results. And afterwards, we are planning to make modifications in design using optimization techniques and validate them using experiments in the near future. So this is everything I had. Thank you for your attention. And if there are any questions, we will discuss them after Francesco has presented.
So yeah, please keep your questions. We'll just dive into the next project and talk about high ramping flexible operation. And what we're doing in the water power lab in this project is to actually look at the possibility of to define the cost of flexibility. And the only way we can address that question mark is actually to look at the materials. And if you look at the fatigue on the materials, we are able to actually say something about reduced lifetime. And if you know, if you can do an estimate of the reduced lifetime, we can say something about the cost. And this is exactly what we're trying to address. For example, just to show you some tests that has been going on earlier here, Johannes Carno did strain gauges, put strain gauges into the turbine runner, and then he did this FEM calculations to find out what was actually going on, and then he did measurements in the lab, and he found out that for this runner, the stresses were very high on low loads, while on high loads it was a lot less. We believe that this is dependent on the speed number and also maybe a little bit on the design. So we are going to go more deep into this question mark. Right now, there are three students, one PhD, and Francesco is going to present here, and two master students, or three master students. that are working on this runner, which has been utilized for a lot of research in our lab. They have been doing FEM analysis on it, and they have done an initial test. And the first test they did was spot on between measurements and simulations. They were very happy about it. We are still looking into the uncertainty of it, but again, first test, first trial, and we are very happy about. So it's nice to see they're going on. So, and from now, I'll just leave the word to Francesco, so he can explain more about what is actually going on and what are the aims for the work that you're doing here in the Waterpower Lab.
Okay. Good afternoon, everybody. As I said, my name is Francesco Albicini, and I'm a PhD candidate here at the Hydropower laboratory. And I'm working on fatigue on Francis turbines. And today I'm going to try to explain you something about remaining lifetime of turbines during flexible operations. So first of all, a little bit of background. In general, we can say that the reduction in the service life of a hydropower runner is related or is associated with two main mechanisms. One is mechanical fatigue, and the other one is erosion. Erosion is the combination of different phenomena, like we have mainly sediment erosion, but also cavitation and corrosion. And we can summarize the effect of the erosion as the loss of material of the turbine. And this affect the shape, and so the geometry of the turbine and its structural strength. And on the other side, we have mechanical fatigue. Usually, at least in Norway, the erosion, or at least the sediment erosion, it's not a too big issue, while mechanical fatigue tends to be more important from this point of view. So we can say that mechanical fatigue is the progressive and cumulative damage of a material that is caused by variable loading. And the important thing to understand is that this variable loading can lead to failure for stress levels that are significantly lower than critical design stress. So what you can say if you look at very close to your component is that when this component is subjected to loads that are changing over time, at a certain point you will have initiation of a crack that usually starts from defects that are inside the material, and this crack will propagate driven by the change in the stress over time, and it will cut through your component basically until the cross section that is remaining is no more enough to withstand the load, even if this is way lower than the critical load that has been used for the design. And so your component breaks and it fails in a very fragile way. So it's a kind of it's a very complex and dangerous type of failure, because your component will fail for a stress level that is considered safe during the design phase. So why is fatigue relevant to hydropower? Mainly because it reduces the useful life of all components that are subjected to variable loading. It has an effect also on the civil structure, but I focus more on the runner itself. And the one thing that is important to understand for the runner is that even when the runner is operating at the design condition, so in steady state operation for the design point, so the design flow and head, it's still subjected to variable loading or a load that change. In the best case, this load change in a periodical way. And this is due to pressure fluctuations or rotor interaction. So runners, when they are operating, are always subjected to variable loading, and they are always subjected to fatigue, and this affects the useful life. And affecting the useful life of the runner, it means that we are affecting the cost of maintenance, because I could have unplanned maintenance, and in general, the life of my runner is degrading. in a way that I was not expecting. So another question is, why after more than 10 years of hydropower production is fatigue still a relevant issue? And the answer is double, I would say. So from one side, we have that modern turbines can achieve higher efficiencies, and this is because of a better fluid dynamic design. But to reach this higher efficiency, they require to use thinner blades, and thinner blades are less structurally robust compared to bigger blades that were used in the past. And the other reason is because hydropower plants tend to be operated now differently from the past. And this is because of the presence in the grid of renewable energy sources, especially the ones that are non-dispatchable, like solar and wind. So what happens is that the presence of these sources challenge the grid stability because we cannot control when they produce, or it's hard to control when they produce energy and when they don't. And to have a stable grid, we need to, for each moment, balance the power production and the demand of power. And hydropower is the best, the most suitable technology that we can use to balance the grid. So the way we use hydropower has been shifted from the past when it was mainly base load to nowadays when hydropower is required to balance the grid. And this for hydropower means working more often away from the design point, so in conditions that are called off-design conditions, and to undergo more frequent to transient operating conditions. So for example, in this graph that represents the operating regime of a turbine, the design point could be here at the sufficient point, for example, and then we can have the off-design conditions, for example, partial load and high load. And actually, it's possible to eventually optimize runner also for not only for the best efficiency point, but having a trade-off between good performances also in other working conditions. But of course, we can do this procedure only for a discrete number of operating conditions, not for all the possible combinations. And transient operations mean, for example, changing from different operating conditions or startup procedure and shutdowns. So what is the problem to run in off-design and transient operation? The main problem are the uncertainties, because typically the runners are designed and verified for a limited number of operating points, usually only one, and in general off-design conditions are not well investigated or not investigated at all. And this means that not only that the runner's efficiency is lower outside of the operating condition or the design operating condition, but also that the fluid structural behavior and the fluid dynamic and structural behavior of the runner, it's not well known and can significantly change from the design conditions. And so this means that as a result, in the long term, we don't know what is the response and damage accumulation of the runner to flexible operation. So to summarize, the problem is that the grids need hydropower plants to balance the grid, and as a result, the hydropower plants are required to operate more often in off-design and in transient operations, and this leads to unclear lifetime loss because we don't know what is the real damage phenomenon, or we are not able to quantify it correctly, and this leads to unclear costs of maintenance mostly. So what is already available? What can we already do with the knowledge that we have? Can we estimate the useful time of runner in steady state operation? Usually, yes. It's not easy, but it's possible. Is it possible to estimate the lifetime in flexible operating conditions? Only partially, and with very coarse precision. So more no, yes. There are two main existing approach. One is on-site, so based on strain gauge measurements, and one is numerical. They both have some pros and cons, but so mainly measurement made on-site with strain gauges can only be done for discrete locations on the runner, and they are usually very complex and costly. And the problem to use this result is that they are not very precise in general. We can do some estimation. For example, this is called, or can be called, the relative damage approach. So we measure the stress or the strain in the same location on the runner for different operating conditions, and we choose one reference condition. In this case, for this graph, is the startup, and then we can, since we can say that fatigue is stress driven, we can compare the stress level. If the stress level is, for example, here for the 75% of the full power, 100,000 times lower, we can say that the damage of this operating at 75% is 100,000 times lower than a startup person. The numerical approach can be potentially very more accurate, but it's usually coupled with the standard global SN or fatigue approach that leads to a limited overall accuracy, and has it can be very computationally expensive, and the geometry of the runner must be known. That is something that power plant owners most of the time don't have. So what is my research approach and what I'm trying to do? I'm trying to improve the lifetime estimation of Francis runner during flexible operations. How I'm trying to do that? First, I'm trying to combine the two approach. So I'm using the Francis 99, so the reference model that Ole Gunnar talked about, that we have available both from in the geometry and as an experimental model that I can test in the lab. And I'm running both experiment and the simulation to try to validate the results of my simulation to obtain a high resolution and verified stress field. When we are able to see how this stress field is, we can, for example, assess potential simplification and of the stress field, and eventually, if they exist, identify correlation with, for example, pressure that we can more easily measure around the power plant, basically. And after that, what I'm trying to do is adopt a crack growth based fatigue model. So nowadays, the fatigue approach that is used to evaluate the fatigue life of a runner is usually the standard global approach based on the SN curve. I want to try to move beyond this approach and using the linear elastic fracture mechanics that will allow me to define a critical crack length. So what is the maximum length of the crack on the blade that we can, or that the runner can tolerate to operate safely? And then the ultimate goal would be try to track the crack propagation over time as function of real operating conditions. So what could be the impact of the research for the industry? Well, for hydropower plant owner, it means basically better estimation of the degradation of the runner, and so the remaining lifetime, and this means better operational decision that can be based on the real maintenance cost and improved planning of maintenance. And for turbine manufacturers, the benefits could be that this could be a validated methodology for numerical simulation and of design transit operation, and being able to track the crack growth over time for different operating conditions means that turbine manufacturer could have the ability to design and certify turbines not only for certain operating conditions, but for example for flexible operations. So we could have, for example, heavy duty turbines that are designed on purpose to work in this way, and can and the damage caused during the operations are in this case no. So that's all for me. Thank you.